Hi, my name is Brady Ayala with Cuesta College Tutoring Center, and today we're going to be talking about a physics problem that's very common to Physics 208A and 205A series physics students. It's the block ramp system with friction, and if you are a physics student, you are bound to see this problem again and again and again. It'll be in your practice homework, it'll be in your web assignment, it'll be on your very first midterm. It will be everywhere, so get this down. It's very similar to the block ramp system without friction, so it's a pretty simple setup, but here we go. We're going to go through the steps to solve this problem, and I'll show you exactly why. So the first step, draw a diagram. It seems pretty simple, but most people miss this one. Draw something very big and easy to follow so that your thoughts are very easy to trace. Secondly, make and label a new coordinate system and label the forces. So if you've been to class, which you should be doing, you'll notice that for these systems we don't have an x and y axis going, x here and y there. We have to tilt this thing to make our problem easier. So we're going to make our x-axis parallel with the plane, and our y-axis perpendicular to the plane. This is just like we did with the ramp system with no friction, so it should be second nature by now. Alright, and now we have to label forces. So here we go. We only have one force due to the mass, but we can now break it up into components that are in the x and y plane. And because this thing is not moving vertically or along this this vertical axis, now we can find the normal force from there too. So we'll label normal force, and then we'll also label the forces that are propelling this down, and the forces that are perpendicular downward this way. So we're going to do a triangle, just like this triangle. It will be a mirror image triangle of this one that's just rotated. Which means that this theta is equal to this theta, this is 90 and that is 90, and then these two angles will be the same as well. So here's mg. mg always acts straight down, and then there's a component of mg that is causing this mass to slide down. That'll be mg sine theta from our previous videos. And there's a component that is going perpendicular to the surface. That will be mg cosine theta. And so, by Newton's third law, for every action there is an equal and opposite reaction. If we have a static system, we know that there's going to be a normal force. Going straight up, it will be equal and opposite to the mg cosine theta. And so that's how we want to set it up. This is set up just like a block ramp system with no friction. And now we want to solve the system without friction to determine the direction of friction. Now, we know the direction of friction right off the bat from here, but it won't always be obvious. So sometimes you will have a force that's pushing this way, or a force pushing this way, and you're not really sure if the force is large enough that friction has changed direction, and you have to actually solve the whole thing without friction, determine if the friction is pointing up the ramp or pointing down the ramp. And the reason why we've got to do this is because friction is always going to oppose the direction of motion. So if we have a force that is going to make this block move up the ramp, then we know friction is going to be pointing downward. But if there's no friction here and we have no forces acting on it, then the block's going to slide down the ramp without anything opposing it. So if we put in friction, it's going to be opposing the motion. It'll be pointing up the ramp. So this is just to kind of get you guys used to seeing how things would behave if there wasn't any friction. This is going to be really important for your web of science later on to determine the direction. Because a lot of times people have these equations down, they have it set up right, but they just have friction pointing in the opposite direction. And you get an unreasonable result. You end up with an acceleration down the ramp that is greater when there's friction than when there's not friction. And that just doesn't make sense in the real world. So watch out. Okay, so by inspection we realized that the force of friction has to be up the ramp. So here we go. Call that F sub F, force of friction. Okay, we've done that. We solved the system without friction, determined the direction of friction. Okay, we didn't actually solve numbers, the exact, but we found out the direction of friction was up the ramp. So now we'll go on a step forward and label the friction force with a direction. Okay, we got it. And to be more accurate, this will be exactly parallel up the ramp. Okay, now we have to write out the sum of the forces in the x and the sum of the forces in the y equations. And as you recall, our x is now this way, our y is now this way, our x is parallel to the plane, our y is perpendicular to the plane. So let's just write out two equations and see what we come up with. Okay. So we know that the sum of the forces in the x is not going to be 0. And the reason we know that is because there is an acceleration down the ramp. So if we have an acceleration down the ramp, and that means that the sum of forces is going to be ma, and mass times whatever acceleration it has. However, if the force of if this force of friction, say this is the force of static friction, and I want to find the minimum mu sub s to keep it static, then it will be 0. So that'll be our first case scenario. So let's build on that. We'll say this is the force of static friction, F of F sub s. So we can find the minimum mu sub s, or the minimum coefficient of static friction, to keep this block from sliding down the incline. So let's do it. Let's say minimum minimum mu sub s for the block to not slide. All right, in this case, with a static system, the sum of all these forces has to be 0 because there's no acceleration. So let's do this. We have the force of friction going up, positive, and then negative, we have mg sine theta going down the incline. And we know that that the sum of all forces is m times a. But if it's static, it's not going anywhere, that means the acceleration is 0, so the sum of forces has to be 0 as well. So this whole thing equals 0. Now we'll do the sum of f sub y, all the forces in the y direction. That has to be equal to 0 as well. So we'll say that the normal force minus mg cosine theta has to be equal to 0. Okay, great. Now, it looks like we have two equations, okay, and we also have a problem now, because we have f sub n in one equation and f sub s in the other equation, and if these two really can't relate to each other, then we're going to have some difficulty. But we do know one equation. We do know that the force of static friction is equal to mu s times F sub n. Great. And now we can just make a substitution. And then I'll just take this one more step and say mg sine theta equals us times the normal force. And I will say that mg cosine theta equals the normal force. So I just added this on one side, and I just added this guy on that side, and that's how I got these two equations. So I have two equations, and what I'm really trying to solve for is the minimum mu sub s. Okay. Now there's plenty of ways to solve this equation. If you've been doing math for some time, you probably want to do something like substitution, and substitution is fine. But for this problem, there's an easier way to do it, and you want to get really proficient with systems of linear equations. You don't have to know all the tricks and all the techniques, but know that you can divide equations by each other. You can set up matrices. You can add these guys together. You can do a lot of things. So if you see a really quick way to go right to the answer, do that. Go for it. And a lot of times in these problems, you're going to be dividing by equations or adding them together. So I'm going to take this one, equation number 1, and equation number 2, and put them together. So here we go. mg sine theta equals mu s f sub n. We'll say that mg cosine theta equals f sub n. All right. And now there's something really cool that we can do with these equations. We can divide them by one another. So here we go. We'll just divide mg sine theta by mg cosine theta. Here we go. The mg's are going to cancel out, and we'll have a sine theta over cosine theta. And sine theta over cosine theta, of course, is tan theta. Okay. And the f sub n's are going to cancel out. Fn divided by fn is 1. And we're left with mu sub s. Okay, great. So that means if I want the coefficient of static friction necessary to keep this thing from sliding, I don't need the mass of this object. And I don't need the normal force. I don't need what its acceleration would be down the incline. All I need is this angle. So mu sub s is going to be the tan of theta. And that's that's it for solving a system with static friction if you want to find the minimum coefficient of static friction to keep it from sliding down the ramp. I'm Ray Aiello with Cuesta College Tutoring Center.